Hello everyone, my name is Prashant and today I am going to discuss about microwaves in quantum computing. Okay, let's start. Introduction. Quantum computing is an emerging field of technology that leverages the principle of quantum mechanics to perform complex computing. While classical computers use bits to represent information as binary digits, zeros and ones, quantum computers use quantum bits or qubits, which exist in superposition representing both 0 and 1. But unlike binary or unlike classical computers, it represents 0 and 1 at the same time, that is simultaneously. This fundamental difference allows quantum computers to perform certain calculations exponentially faster than classical computers for specific problems. For example, cracking our network. So our access to the internet is protected by a small padlock that we can see called encryption. So for classical computers it may take tens of thousands of years or even lakhs of years to break, but for a quantum computer it takes just a couple of hours to break our encryption. So quantum computers are really powerful machines. So what are microwaves? Microwaves are form of electromagnetic radiation with wavelengths ranging from approximately 1 millimeter to 1 meter. They fall in the frequency range between radio waves and infrared radiation on electromagnetic spectrum. Microwaves are commonly used in various technologies and applications, that is, micro ovens for cooking and heating food quickly. Moreover, microwaves also play a vital role in telecommunication and wireless communications, enabling data transmission over long distances. So with these, additionally, they also find applications in scientific research, radar systems, and industrial processes. So now let's discuss about how microwaves are used in quantum computing. So microwaves are an essential component in certain types of quantum computing systems, particularly those based on superconducting qubits. So microwaves are used to manipulate the quantum states of particles like electrons or photons. These microwave signals are used to apply precise electromagnetic field to qubits. So basically qubits are the basic building blocks of quantum computers, like for binary 0 and 1. So for quantum computers it is qubits, allowing for operations such as qubit initialization, single qubit gates such as rotations, and 2 qubit gates such as entangling operations. Microwaves are used to read out the results of quantum computers and quantum computations that it calculates. So creating qubits with microwaves. So microwaves are used to create qubits by manipulating the spin of electrons. This is done by using a magnetic field and a resonant microwave frequency. So qubits are created in this way are called spin qubits. So, manipulating qubits with microwaves. Microwaves are indeed used to implement and control qubits in certain quantum computing architectures, such as those based on superconducting circuits. The interaction between microwaves and qubits is achieved through carefully designed circuits that couple the qubits to microwave resonators. So to manipulate a qubit using microwaves, specific microwave pulses with defined frequencies, amplitudes, and durations are applied to the resonator connected to the qubit. These pulses are designed to have specific effects on the quantum state of the qubit. So, for example, microwave pulses can be used to initialize the qubit to a known state, such as preparing it to a superposition of 0 or 1. This is achieved by applying a carefully tailored pulse that puts the qubit in desired state. Microwaves are also utilized to implement quantum gates, which are fundamental operations that allow for transformational and entanglements of qubits. So, reading of qubits with microwaves. So, reading of qubits in certain quantum computing systems, such as those based on superconducting circuits, can indeed involve the use of microwaves. To read out the state of qubit, the qubit is coupled to a microwave resonator or cavity. The qubit state affects the resonator's properties, leading to a measurable change in the microwave signal transmitted or reflected through the resonator. This change in the microwave signal provides information about the qubit state. So, the readout process typically involves application of specific microwave signal to resonator and measuring the resulting signal. By analyzing the characteristics of microwave signal, such as its amplitude or phase, it is possible to infer the state of the qubit. The readout process can be performed by using a technique called dispersive readout or by utilizing quantum limited amplifiers to enhance the sensitivity of the measurement. So, in summary, microwaves are used in the readout process of qubits in certain quantum computing systems. By coupling qubits to microwave resonators and analyzing the resulting microwave signals, it is possible to determine the state of qubits and obtain the outcomes of quantum computations or measurements. So, challenges in using quantum computing. So, while microwaves are a valuable tool for manipulating and reading of qubits in quantum computing, their use also poses certain challenges. For example, decoherence. Qubits are highly sensitive to environmental noise and decoherence, which can degrade the coherence and reliability of quantum information. Microwaves used for qubit manipulations and readout can introduce unwanted noise and interference, leading to increased decoherence and reduced qubit performance. Crosstalk and leakage. In multi-qubit systems, microwaves used for qubit control and readout can unintentionally affect nearby qubits. This crosstalk or leakage can lead to unintended interactions and errors, impacting the accuracy and fidelity of quantum operations. Microwave loss. Microwaves can experience losses or attenuation as they propagate through circuits and resonators. This loss can limit the efficiency and coherence of qubit control and readout operations, affecting the overall performance of quantum computations. Scalability. Scaling quantum systems require increasing the number of qubits and their connectivity. However, as the number of qubits grow, it becomes more challenging to design and implement microwave control systems that address all qubits individually and mitigate crosstalk issues effectively. Quantum limited amplification. High fidelity qubit readout often relies on sensitive microwave amplifiers that operate near the quantum limit. Achieving low noise amplification without introducing additional decoherence sources can be technically demanding. Microwave So, applications of quantum computing with microwaves. Quantum computing with microwaves have the potential to impact several fields and applications. Here are few notable areas. So, for example, cryptography and cybersecurity. Quantum computing can potentially break current encryption methods, including those used in secure communication and financial transactions. Machine learning and AI. Quantum computing can offer advantages in machine learning and AI by leveraging quantum algorithms like quantum support vector machines or quantum neural networks. Quantum chemistry and material sciences, the simulation of molecular systems and complex materials in an area where quantum computing with microwaves can have significant effect. Quantum optimization and simulation. Quantum computing has the potential to revolutionize optimization problems in various industries such as logistics, finance, and supply chain management. So, quantum computing companies using microwaves. So, there are several companies working on developing quantum computers using microwaves. So few of the companies that include are IBM Quantum, Google Quantum, Rigetti Computing, and Ion Q company. So each company has its own approach and architecture for building quantum computing. So, future of quantum computing. The field of quantum computing is still in its early stages. Researchers are trying to improve the reliability and scalability of quantum computers. In future, quantum computers with microwaves could solve problems that are currently impossible for classical computers. Conclusion. Thank you.